Let me start. If I walk up to you and give you a system of linear equations, one of the big things we know is we can write this as an augmented matrix, right? And oftentimes it's easier to compute things when we write them in the augmented matrix form. And I'm going to give you a special type of linear system. A system of linear equations. Is homogeneous. Yeah, written in form a expression. By the way, on quizzes and homeworks, when I write this out in type form, instead of putting a little hat over the vectors, I'll usually put it in bold. So a bold X we usually mean a vector when I write it up on the quizzes, as opposed to having a hat on it. What does this mean? All this means is the set of linear equations. Every equation equals 0, right? So, for example, that's a homogeneous equation, just because all these are zeros, right? Now, this might seem like, oh my goodness, why are we making definitions for this when it's all zeros? Because the homogeneous equations actually have a very special property that we can see. And notice the matrix form for this would be in this case, the matrix A would be 1, 2, 1, 0, 1, minus 1, 1, 3, minus 1. And back to this. And here's the C. So that's it. A homogeneous equation is just one where instead of AX plus B, we have the special case AX equals 0. Let me make a little mark. And I actually mentioned this last time. So this, of course, it's homogeneous, but there's 0 back to on the right side. This always has a solution, right? That's the first thing about homogeneous equations or homogeneous systems that's important. This is different from in general, because remember, sometimes we get unlucky and we have an inconsistent system. Oops, no solution, right? For homogeneous, always at least one. Right, tell me what it is. What can you plug in for X vector of the Homogeneous equation? 0. There you go. So, ding, 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 homogeneous equations always have one solution. And of course, the big question that you ask then is, does it have one or does it have infinitely many? Right. Let me point out, this is one of the first things that we said in class when we first started out, right? That if you have a system of linear equations, then what happens? Well, it's either inconsistent, it has one solution, or it has infinitely many. Y'all remember that? Well, homogeneous equations always consistent, right? There's always at least one. Why is it now? This is kind of a first peek into why it is if it has one solution, which it doesn't. If it's got more than one, why does it have incomplete many? Let me remind you of something that I told you about at the end of last class. If A, this is easy to verify. So this is actually here I'm talking about the last section. So A is an n by n matrix. Let's say that U and P so these are in n-dimensional column vectors, and C is a real number. So let me read the symbolism here. A, n by n matrix with real entries. U and B, an n-dimensional vector. And C, just some number. Number one, A what do you hope? Yeah.
A vector U plus A vector.
Right, I hope that too. And look, yes, that's what happens. Two, and this is going to be important. So we're not
Got an extra eraser.
well, we got this one. Yeah. I don't know what's up. Yeah, I've only got one. So, what is CD? Remember what it is. B is an n-dimensional vector. When I multiply by C, it's just a vector that I've stretched, right? All I've done is multiply the coordinates by C, right? So this is also an n-dimensional vector. Anybody want to guess what I'm going to write on the right side here? Okay. You can pull a constant. This is actually quite important. Because somebody, this second one right here shows, let me make. We have zero has more than one state. And it has. So this is kind of the first kind of look at why this crazy fact that I told you actually holds true. And this is kind of a strange thing. This doesn't happen for things that aren't linear necessarily, right? Quadratic equations, for example, can have two solutions, right? There are, if you intersect two curves, it can have any number of solutions. But when you intersect, or when you have systems of linear equations, if you have more than one, you have to have infinite many. And this is kind of the first look at that. Anybody want to? Why is that? Why is that the case? I'm actually kind of prove this is a little more of a computation. Actually, just let me say D was there was one solution to make this question. We've already established that. I can plug in B equals 0 to that X, and I get 0. Everybody okay with that? if there's more than one solution, so if there's another solution, then somebody make a simple observation about that. I know that the zero vector is a solution. So if there's another solution, what can I say about it? Well, that's right, but see, that's what we want to show. We don't know that. Actually, I'm looking for something really kind of dumb.
Let's say two dimensions.
Well, so would you agree with the following statement? If there's a solution that's not the zero vector, well, if there's more than one solution and one solution is a zero vector, this one is not the zero vector, right? And what does it mean for a vector to not be the zero vector?
In this case, it's a scalar multiple.
Okay.
Is that
You
what
guys are
you're
on.
trying to get at?
So there's another solution y that's not the zero vector. And what does it mean to not be the zero vector? It means that y at least one of these entries in the column can't be zero, right? One of them has to not be zero. We'll say this one, just for giggles. I agree. Now, let me point out that AY is the zero vector, right? And if I multiply the zero vector by any constant, what do I get? The zero vector. Correct. And this thing is like a vacuum cleaner. It suck that C right inside there. So any multiple, I think you pointed that out, any multiple of y is also a solution. Everybody agree with that? And since this entry is not zero, when I multiply this by any constant, it's still not zero, as long as that constant's not zero, right? So this could be infinitely many things here, and so there have to be infinite solutions. Everybody open? So there's our first look at this. Y, zero vector. Then there are infinitely many so as we vary C, there's infinitely many of these solutions. The homogeneous. Now, I still haven't done this in general for the non-homogeneous, but that's also true, and we'll see that later. Okay. Any questions? Yes.
So whenever you have a free variable as well, there's many solutions because like everything else. is not free variable.
That's exactly right. And in fact, that's what it's going to boil down to, just like we've seen before. When we put this system into a matrix, figure things out, it's going to boil down to does it or does it not have a free variable for the homogeneous case. So let's look at an example here. Let me just start with a homogeneous equation, and then I'll show you how to do things in general. Let's look at this system of equations. Let's say 2x1 plus x2 minus x3 is 0. x1 plus x2 plus x3 is 0. and 3x1 minus x2 minus x3 is equal. Okay. Now, I'm gonna do this one, and then I'm gonna do a variant of it. I'm gonna do just right quickly. Notice, of course, it's homogeneous, and so if you let the values of x1, x2, and x3 all be 0, that's a solution. That's essentially the 0 factor. So let's see what we get here. Let's do the augmented matrix. 2, 1 minus 3, 0. By the way, I love doing augmented matrices for homogeneous because it never changes the right column. Yes.
The -3 be a -1.
Yeah, thanks. 2, 1 minus 1, 1, 1. 0 and 3 minus 1. Okay, so let me I'm gonna use this one because it's one there and I'm a lazy fella. Take out this and this. So in my next step, I'm gonna have the same middle row. 1, 1, and 0. To nuke the top, I'm gonna multiply this by -2 and add. 2 and add, 2 and add, -2 and add. I love that right column, right? Because it doesn't matter, it's all going to say zeros. That is part of the magic of the homogeneous, and that's why things work out really nice. For this one, multiply by -3 and add. Times -3 and add, -3 and add, and again, 0. Okay. Now, I'm gonna clean this up just a little bit, just so it's a little bit more pleasing to the eye. I'm gonna put the middle row on top, and I'm gonna turn this to a row of all ones in the middle. So put this on top. Then I'm gonna divide this by -4 and put it in the middle. And this one right here. Oh, and I'm gonna put that positive 0.3. Yes,
Where do you get the 1, 1 from? 0, 1, 1?
dividing this by -4. Other questions? And now, actually, I just take one more step. I get to try and make it so it'll be easy to see what the solution is. 1, 1, 1, 0, 0, 1, 1, 0, 0, 2. Now, how many solutions does this have?
1.
One and only one. Namely, the 0 vector was the only thing that worked, because this last one, what it means is 2x3 is 0. I know x3 is. And now x2 plus x3 is 0, but x3 is 0. So that means x2 is 0. And finally, x2 and x3 is 0. On top of which is x1 plus x2 is x3 is 0, which means that x1 is 0. So that's it. The 0 vector is a solution to that homogeneous system, but it's the only one. Everybody okay? Now, let's look at system right here. Then I'm going to change this one. Here. Let's first look at this. X. This time, yeah. that's still. 3x1 minus 2x2 plus 5 3 0 and x1 minus 9x2 plus 5x3. Okay, so let's look at this. Again, like before, it's homogeneous, so for sure I've got all zeros, zero vectors solution. So let's turn this into an augmented matrix and see where to get from there. 1, 1, 0, 3 minus 2, 5, 0, 1 minus 9, 5. Okay, let's see what happens now. I'm going to take the top row. I'm going to take that one up in the upper left corner and use it to take out these numbers here. So I'm going to multiply the top row by -3 and add it to the middle row. That gives me a 0. That gives me a -5. That gives me a 2. Yes.
So is it impossible to have a non-homogeneous equation listed as constant?
I'm sorry.
Is it possible to have like one that's not a form where they can all be zeros unless there's a constant, basically? Because unless there's a constant, it looks like it's always going to be true that you can have every single one of the variables be zero.
Yeah, and that's the point, right? If you have a homogeneous solution, you've always got that.
Okay.
Now, in the previous example, that's all we had. It was only the zeros. In this example, we'll see something a little different happen. We certainly have a zero solution, but do we have more?
Okay, might have.
And that's gonna actually, that's a nice segue into the example I'm gonna do next. But
Okay.
so let's multiply this by -1 and add, -1 and add, -1 and add. Now, what do you see about the rows here? Yes.
The last row is gonna cancel out to be all zeros. By the second row by -2.
Right, right. So this, in this case, what's going to happen is actually we're going to have more solutions. And so let's kind of work through this in more detail. Right, because I can multiply that middle row by -2 and add it to the bottom, right? So it's gone, as you point out. And this is an indication, of course, I get consistency here so far, and it should be consistent because I know the one solution. And this is a big indicator that I have multiple solutions. Let me multiply the middle row by -1/5. So I'm going to bring this all the way to row reduced echelon form. And to make this as easy as possible, I'm now going to add, I'm going to multiply the middle row by -1 and add this to make the row reduced echelon form, and that's going to be 7/5. Okay, 3 variables, x1, x2, x3. How many are basic? 2, namely the x1 and the x2 are basic. 3. And the one that corresponds to the non-pivot column, the one that's on the right, well, next to the column zeros here, x3 is our free variable. So I'm going to write this in kind of a Brown trial vector form. This first equation gives me x1 plus 7/5 x3 0. And the next equation gives me x2 minus 2/5 x3. So I can write these equations. X1 is minus 7/5. X3 and X2 is 2/5. X. So I can actually write this in a convenient vector form this way. What is my solution? Set the homogeneous. There it is. That's me being a bit of a smart aleck, right? Because that's just X1, X2, X3. However, the equations tell me everything I need to know. X3 was free variable. It can be anything I want. So there it goes. Just doing this free thing. X2 is 2/5 of X3. And X1 is minus 7/5 of X2. So any solution to this looks like this. Put whatever you want in the bottom, and then take 2/5 of that and put it there. Take negative 7/5 of that and put it at the top. Notice if I take X3 to be 0, I get 0, 0, 0, which is the solution that's not polarizing. And of course, another way I can write it is this. X3 can be anything, so I can pull it out. Negative 7/5. 2/5. And actually, if you don't like fractions, for whatever reason, you could pull out 1/5 X. Because since X3 can be anything, 1/5 X3 can be anything, right? And you can write it in this G form, maybe. So basically, any vector that satisfies this ratio, right? Three entries satisfy this ratio of things, right? 1 to 2/5 to negative 7. Well, that will be a solution to the homogeneous equation. And here's another thing. You were asking on the chat board last night about the good thing about this is if you're not comfortable with it, go back and plug it in. You can check it. These things are always checked, right? And even though you may not have time to always check things on a test or quiz, you do on homeworks. Okay, any questions? Okay, so homogeneous, we've done the homogeneous, right? Let me show you how to deal with the more general situation. And actually, it turns out, so I'm gonna make a prediction, and then I'll show you how to compute it. You'll see it come to fruition that way. Okay, suppose I have this more general. So now B is not necessarily 0. Suppose I have this equation here, right? And let's suppose that I actually have a solution, right? I mean, if you don't, it's kind of problematic, but let's suppose you actually have a solution. There is a particular solution. We'll say B. So there's some solution somewhere which we call B, because consistent means there is any solution. Okay, so there's one solution. Any solution is of this form. it is this solution plus a constant multiple of u, where C is in real numbers and U is a homogeneous solution. That is to say, A, U. This is a cool little result because what it says is, if you find any solution to this, then any other solution is just the solution you found plus a multiple of the homogeneous solution, right? Let me ask you this. What if the homogeneous solution only has one solution, only the zero vector? Then U would be the zero vector, and that means that there's only one solution. If, on the other hand, the homogeneous equation has infinitely many solutions, then this has infinitely many solutions as well, right? Because start with any one you want and then just add the homogeneous solution. The particular solution is not necessarily unique. So let's see this in action. I'm going to do this in two parts here. So let's start off this way. Let's do this. 3, 2. By the way, I better be careful because now, and this is what you were talking about earlier. Now I'm putting numbers in here that are not zero. I'm not too sure that this is going to be consistent if I just make something up at random. In fact, it's probably not. So let's call this A. Question first. For what A is this consistent? And then for this value, find the solution. Okay. Everybody okay? First thing, and let me put this in matrix form. 1, 1, 1, 3, 3 minus 2, 5, 2, and 1 minus 9, 5, 8. Right? And what I want here is consistency. I mean, crying out loud, I want a solution in the first place, right? Okay, so I've got the system of equations. So let me just, I mean, steps here, since we've already done this homogeneous, will be pretty much the same as what we did before. It's just, I've got to muck around with this right column, right? Could be different. Okay, I'm going to multiply by minus 3 to take this out. That's going to be minus 5. That's going to be 2, just like before. So all the stuff over in this part of the matrix should be the same if I do it right. This, however, should be -7 times -3.5. Right? Let's multiply by -1 to take this out. Again, just like before, 0 minus 10, 4, multiply by -1 and add A minus 3. Okay. So now I think this is kind of a crucial moment when we notice, hey, this thing takes this out, right? So let's see what happens here. 1, 1, 1, 3, 0 minus 5, 2, -7. And we'll see, what do I need to do to take this out? I got to multiply by -2 and add. It's -2 and add. It's -2 and add. So it's going to be 14 minus 3, A plus 11. Everybody okay so far? Now, can somebody riddle me this? Can somebody answer the first question? Yes,
It would have to be -11. because you
that is
have
correct.
letters.
That's right. You can't have a pivot column down here, right? So in other words, when you have the zeros and variables, this has to be 0 to have a pair of consistency, right? So I need A plus 11 to be 0. So let A equal -11. Oh, Taylor, can I see that once? Not good. A is -11. So let me just kind of correct this over here. And that's that. Okay, now proceed, right? So I'm gonna do what I did before. This is now 0, convenient. Multiply this by -5, and I get 1, 1, 1, 3, 0, 1, -2/5, 7 fifths. And 0. And so now yeah, 1, well, 0, 0. Well, we got 1 -2/5, 7 fifths. Right. And I'm going to take -1 times the middle row and add it to the top. So I'm going to get 1, 0. That's going to be 7 fifths. And let's see, that's going to be 15 fifths minus 7 fifths is 8. Everybody okay with that? Now, I'm very self-pleased with myself right now because we've got a row reduced echelon form. So now we're near the end game. So what this says is x1 plus 7 fifths, x3 is 8 fifths, and x2 minus 2 fifths, x3 is 7 fifths. Now, just like with the homogeneous, I've got x1 and x2 are basic and x3 is free. Do I get with that? And so it's the same kind of situation. What I have is x1 is 8 fifths minus 7 fifths x3. x2 is 7 fifths minus, or I'm sorry, plus that. And so if I were to write this out in a parameterized form, then it would look like this. This is very similar to what we did before. X3 is free, so just sit there being all free and stuff. X2 is 7 fifths plus 2 fifths x squared. 7 fifths x3. And x1 is 8 fifths minus 7 fifths x3. Everybody okay with me? And now I can pull this apart. Everybody see what I did? If you put this back together, we have 8 fifths plus x3 times minus 7 fifths at the top. In the middle, 7 fifths plus x3 times 2 fifths, and in the bottom, 0 plus. Everybody? This is, in my remark, what I call the particular solution. If you plug in 8 fifths and 7 fifths and 0, you should get a solution to this system. Right? For example, 8 fifths, 7 fifths, 15 fifths, which is 3. Check it, it will work. Does this look familiar? This right here, this is the homogeneous part. And this is the particular part. And it always works this way. You can just kind of pull it apart. Any questions? Let us attempt one more. I'd like to kind of go one of these. So let me give you the following system of equation. X2 plus X3. X2 X1. X5, X9, X1 plus 2X2 plus X3 plus 3X5 X1 plus X2 plus X3 plus X4 plus 2X5 is 8, and X1 minus 7 X2 plus X3 plus 5X4 minus 2X5. Okay. So here, we'll just do the computation. I mean, hopefully, and again, this is a system of linear equations. It's not homogeneous, so it might be inconsistent, but we'll see. So let's do this thing. This 1 minus 1, 1, 2. 1, 2, 1. 0, 3, 5. Looks like 4 1s and 2, 8. And 1 minus 7, 1, 5. Minus 2. All right, so let's work through this. The first thing I'm going to do is I'm just going to leave that top row alone because it's already there. So I'm going to leave the top row alone back for now. 2, 1, 9. And I'm going to use that to take all these out. So that's going to be 0, 3. Hold up my minus 1 and add 0, 3, 0, minus 2, 2, and negative 4. That's minus 1 and add here. So 0, 2, 0, minus 1, 1, and 1. And minus 1 and add all the way down here. Let's move 0, negative 6, 0, 3, and negative 3, and 3. Now, I can actually simplify my life a little bit. So let me not have to write everything out. Let me replace this row by 0, 2, 0, 1 minus 1 minus 1. That is dividing this by -2. Or I'm sorry, dividing this by. Divide that by -2. It should be -1 plus. And notice these two rows are the same, so I can take that out. And this brings me to 1 minus 1. 2, 1 minus 1, 1. 2, 1, 9. 0, 3, 0, minus 2, 2, minus 4. 0, 2, 0, minus 1, 1, 1, and a row of zeros. Now, I will do something here to make my life easier. Because of the similarity in the shared zeros, I'm going to multiply this row by negative. Right, by -2 and add it to this one. Right, so I'm going to multiply this row by -2 and add it here. And so I'm going to get 1 minus 1, 1, 2, 1, 9. And I'm going to have 0, 2, 0, minus 1, 1, minus 1. This row right here. Now, multiply this by -2 and add it here, so it's -1, 0, 0. And that's kind of point.
How's that negative?
I'm sorry,
How's that negative?
multiply this by -2 and add it here. So
Sorry, I thought you said -1.
-2 here, -2 here. So -2 here. It's minus 2. Yes.
I think the second row, second from the left column, is supposed to be positive, right?
Are you talking about second row? So that's going to be -1. That's going to be 0.
Second row, second column,
Second row, second column.
shouldn't that be positive? One, not negative.
No, I'm multiplying this by -2 and add it here. So it's -4 plus 3. It's negative.
Oh, okay.
So this one, by the way, I already know that x2 now 1, isn't it? And actually, I can use this to clear this out and see, since we're running out of time, work through the rest of this, and I will hopefully tell you what I got. I got the following. 1, 2, 0, 5, 0. 1, 5. In this case, I end up with 2 free variables. And the free variables are x5. I'm sorry, x3 and x5. And I get and -3, 0 to 0, 1. Yeah, that's what I. So, see if you can work through this, and if you can't, go by my office and we'll work on it through it as well. Any questions on it? Any questions? Bye. If I don't see y'all, have a good weekend, and I will see y'all Monday.